Okay then, let me just go to the clock here. So you have 10 minutes. Have a nice presentation. You can start now.
Okay, so I am Max Rupšev from Slovenia, and I will be presenting problem number 8, heavy parachute. So the problem asks us if it is possible to build a magnetic parachute to protect the load from impact when landing on a non-magnetic metallic surface. It goes on to ask how should it be built in order to minimize the impact damage and what are the limitations of our parachute. So in our solution, we try to determine if a magnet can minimize the impact the magnet itself experiences when falling on a conducting plane. We devised a theoretical model based on eddy current interaction with the magnet using a method of mirror images, and we used it to test our question. We used the simulation. We used the model for a simulation to estimate if the mechanism is possible to optimize it, find the best possible setup. We conducted a small experiment to test our model. All along, we assumed that the magnet's bottom surface should be flat to maximize the proximity of the plate, that its shape in projection doesn't have a big effect, that it is always falling horizontally and never rotating, and that the landing surface is an extremely good conductor. So our theoretical model observes a cylindrical magnet appears at a distance above a conducting plane with no velocity. The eddy current it induces are equal to the magnetic, create a magnetic field equal to the magnet's mirror image. That is under the assumption of an ideal conductor. In regular conductors, the eddy currents disappear very quickly, and mirror images are not perfect. So we used the mirror image method to calculate the movement in discrete steps. We used the equation for the force between two identical cylindrical magnets that was calculated by Vokun and others. We numerically integrated the kinematic equations, and using the equation you can see on the screen for the acceleration with respect to the parameter zeta. Now, the parameters for in our equations are the main parameters are the aspect ratio of the cylinder. We use the simulation to find the relation between the specific dissipated energy with respect to tau. Using that, we found the optimal parameter tau, which was equal to 0.43. The density of the magnet should be minimized, as well as the size of the magnet to reduce the mass. The presence of the load on the magnet that we are trying to protect, we solve that by introducing the effective density. And the specific dissipated energy gives us the maximum velocity that we can absorb and the maximum drop height through two very simple equations. We plotted the maximum height of the drop with respect to the magnetization squared per height of the magnet. The graph shows us that the parameter magnetization squared with respect to the thickness of the magnet should be maximized. We use that to get the absolute limitations of our parachute, but we need to be aware that for finite plate conductivity, the performance of our magnet could only be worse. We simulated, can you see the next slide? Okay. We simulated the dropping of a 150-gram magnet with a radius of 2 centimeters with optimized tau, so that gives the height of the magnet that was dropped from 25 centimeters above the plate. Now, as you can see from the velocity graph, the magnet only starts breaking very late in the falling process, which causes extremely high accelerations to be felt by it, which could damage the load and negate the and harm the load in the process, which would render such parachute unusable. We tested our model by dropping a N42 neodymium magnet from different heights. We then analyzed the motion. We dropped magnets of different dimensions. A smaller magnet with a magnetization of 2 times 10 to the 4th ampere per meters and mass 1.1 grams, and the bigger one with mass 37 grams and magnetizations around 2 times 10 to the 5th amperes per meter in different configurations. So we tried dropping a single magnet above a plate. We tried dropping 2 vertically stacked magnets, large and small. Now we dropped them on 2 vertically stacked plates, a copper one with a thickness of 0.2 centimeters and an aluminum one with a thickness of 0.5 centimeters. Now we noticed that the thicker the plate, the better the effects were. We then used the magnetometer to measure the magnetizations that I gave you previously. And on the screen, you can see a table for the experimental parameters for the larger magnet. So I will show you the videos of the magnet being dropped from 5 and then around 17 centimeters. So this is a magnet. Okay, I see it isn't going to work right now. So we could hear a slight difference in sound when the magnet landed when being dropped from 5 centimeters. We could hear a difference from only dropping it on the ground, but the difference was not observed when dropped from higher. So we analyzed the footage. I'm having some trouble with the presentation. So we analyzed the footage. The footage when dropped from 5 centimeters and 16.4 centimeters. Now, as you can see in the left graph, there was a slight change in the slope of the graph at the end, which is a result of a slight slowing that we could hear. However, when dropped from higher, like 16.4 centimeters, for example, the magnet showed no real slowing effect. And these two graphs are for dropping the magnet from dropping just a single magnet on the previously described plate. Now we repeated these measurements, this time stacking 2 magnets top of each other. We noticed that the magnetization of the magnet rises slightly, but rises with 2 magnets stacked on top of each other, but not by twice. So the relation is not that simple to find when stacking magnets. So again, you can see that no significant difference was observed compared to just dropping a single magnet, or even dropping just dropping them and letting them fall free. Now, to conclude, we try to find if such a parachute would be possible. For that, we designed a model using eddy current interaction with the magnet that produced them, using mirror image methods, and then found the force between 2 identical cylindrical magnets. We looked for possibilities of that using the best possible conditions. So using a plate with a very high conductivity, dropping just the magnets without any extra load. We found the parameters that impact the performance of the parachute. So that would be tau and the ratio magnetization squared over height of the magnet. We optimized when possible. So per tau, and for magnetization squared per unit length was also found to be as big as possible. Now it's limited by the fact that the conductivity of the plates are finite, and we also were able to test if a superconductor can stop a very small magnet in midair, and we found it to be possible. Sadly, I cannot show the video right now. So thank you.
Thank you very much.
So this is Sabahuddin Ahmed from Pakistan, and I will be opposing the problem number 8, heavy parachute, just presented by the team Slovenia. I hope I'm audible, right? Okay, so
yes, your time is already going.
Yeah, so if we stick to the problem statement, and I just want to reiterate the problem statement, it's that if the problem statement asks us that is it possible to build a magnetic parachute to protect the load from impact when landing on a non-magnetic surface, and how should it be built in order to minimize the impact damage, and as well as what are the limitations of the parachute. So I would just now move towards the summary of the presentation. The reporter from Team Slovenia, they presented a moderate theoretical model for this phenomena, where they mentioned the eddy currents as well as how the eddy currents are involved inside this whole process of making this possibility of the magnetic parachute possible. And then they performed some experiments, which they they first designed a simulation, and then they performed experiments, and their experiments, then they concluded that their experiments, since the experiments were getting data, similar data as the simulation, so they concluded that their results were conclusive, and they were able to match those results to what the problem statement aimed. Now I would just move towards the remarks. I would say that in light of the problem statement, the theoretic there's a typo. Sorry. Sorry for this. Oh yeah. So in this, I mean, in light of the problem statement, the theoretical model that they mentioned, the brief model that mentioned, where they refer to the eddy currents, and they also presented an equation, and then the aspect ratio of the magnets as well. That that model was a good point, that because they were able to mention the theory as well, and then they moved towards some limited experiments, and then those experiments matched the limit simulation data. And in terms of the points that I think might have been missed, that they did not involve limitations as to what this particular problem statement, or if we just want to visualize a magnetic parachute in the real world, what kind of limitations might have act on that particular parachute. And then there was some missing factors affecting the eddy currents as well. Okay, so with that, I would just want to now move towards the discussion points that on which I want to carry on the discussion with Team Slovenia. I mean, the first point is that do Team Slovenia think, or the reporter think, that the thickness of the copper plate, or the plate, I guess they performed the experiments on by the picture, I can assume that they used the copper plate as their major part for the experiments. Is that thickness at the top is of I mean, is there a limitation on that particular thickness so that it overcomes the skin effect? And then what if they had used some other magnets? I mean, what would happen if we tried different magnets? For example, if there are physical magnets available, such as the N52 magnets, so what would happen if we use different magnets? And what, in their opinion, would happen if the geometry of the copper plate changes? For example, if it's they use a square shape or a cuboid shape plate, but what would happen if it's cylindrical in shape, or what would happen if it's different in shape? And then what's the maximum limit on height? What's the maximum limit on height? And I would want to ask that if were they able to test or get a maximum limit on height, And were they, I mean, they mentioned that they tried different variations of plate. They mentioned the data, but I wasn't able to observe if they tried it with aluminum or other plates. So I would want to, discuss on these points with the team Slovenia.
Should I start the discussion? So first, regarding the copper plate, now we chose or used the 0.2 centimeter thick copper plate because we could only we weren't able to procure a better plate, thicker copper plate, just a practical limitation. Now, is it thick enough to match our model? Our model assumes a very good conductivity, so just in that it overestimates the effect of finitely conducting plates. Now we also assume that the frequency was low enough of the changing electromagnetic field that the skin effect had a limited influence. So that's why we decided to not to account for it. Regarding the different magnetization, like with the thicker copper plates, we could only procure a N42 magnet. Now, as my graph showed, the one with so the maximum drop height with respect to the magnetization squared per thickness of the magnet, the graph, you could stop a magnet falling from any distance if you had a strong enough magnet. However, magnets are not infinitely strong, so as your question with maximum limitation on height, it depends on the magnetization of the magnet. So because the magnetizations are limited, so is our height then limited that we can drop it from. Regarding the question on different geometry of the plates, we assumed that the plates were much larger than the magnet. So we discount the effect of different shapes, different sizes of the plate.
Sorry, I'm extremely sorry to interrupt you. I just want, you particularly mentioned that the thicker the plate or the thicker the, non-conducting metallic surface or the non-conducting metallic plate, the better, the result, response to the magnet in order to slow it down. I guess that's what you mentioned during the presentation, right?
I didn't quite catch the question. Okay, could you maybe repeat it?
I'm saying that you mentioned in your presentation that the thicker the plate, better the effect, the better the resistance from the plate towards the whole system of the magnet and the load. So was that, I mean, did you perform some experiments or was that just a qualitative, assumption or reasoning?
We didn't perform a structured experiment on the thickness of the copper plates. However, when we did try to drop a magnet on just the aluminum, on just the copper plate, and the effects were noticeably smaller. So the sound that we could, the reduction sound dropped on both plates was gone when we dropped only one plate. So that was just a qualitative observation while conducting our experiment.
Right. Okay. I guess it's something that we can test, and it can be an improvement to this particular model, where we can involve this, get multiple different plates and then perform this experiment in real life, so that we can make a proper conclusion regarding this thing. Okay, right. That's great. Okay, so I guess. If, for example, what would happen if it's, for example, you mentioned that you faced a limitation in your, experiments, you were not able to get a proper or strong magnet. So if we get a strong magnet, I mean, will there be a limit on the maximum height? Will there still be a limit on the maximum height, or were you able to find a maximum limit on your height with your N42 magnet that you used, that you were able to, use in your experiments? I mean, is there some theoretical explanation or a qualitative explanation to, get a maximum limit, or do you think that there won't be any limit if the magnet is very strong and it will just have, a resistive effect in every case? I mean, what's your opinion on this?
Now, if the magnet could be infinitely strong, then we wouldn't have a height limitation. However,
now all teams can join the discussion.
Sorry, I lost my train of thought. So, however, magnets are not infinitely strong, and because the reach of the magnetic field is so short, if it were if it were dropped from a very high distance, it could only start slowing down very late, which means that it cannot dissipate enough energy to stop. Moreover, the deceleration would be very strong and possibly damage the load on the magnet as well as the magnet. So yeah, I hope that answers. And regarding the magnets, we were able to get N42 magnet with with magnetizations of around 10 to the 5th magnetizations, which produces fields of around 200 millitesla, which is it's not the strongest magnet available, but it is quite strong. So.
Yeah, right. So I think we can conclude mutually that there is a certain limit at which the magnetic field, if it's properly strong, so we can, assume that to be the maximum limit on height. If it's falling from a very high height and it's not, interacting with the non-magnetic metallic surface or the metallic plate at the bottom, then obviously it will have, it will have a higher velocity while falling towards the metal plate. So I guess we are on the same thought that obviously the limit would involve the magnetic interaction between the magnet and the plate, and there is a proper distance at which if it's dropped, and then that would have a very much strong effect, and we can then save the load. Okay, right, great. Okay, so I mean, yeah, you mentioned, I guess, in your third, in response to my third point here, that you did not, involve the size of, or the shape of, do not consider the shape of your plate, since your magnetic size or your magnet's size was very much less as compared to the size of the copper. So yes, that's a great assumption. But I mean, what would happen if, for example, we have a very, massive or very great a load of a very high volume, and obviously in order to use a magnet with that particular load, we would require, a greater size magnet. So will that account for your model? I mean, what's your opinion on this particular point? That, for example, if the size is comparable, if the size of the metallic plate is comparable with the size of the magnet, then will this, geometry affect this whole phenomena or not?
So our model assumes that the plate is much bigger than the magnet. I do agree with you that a factor that would take into the account if the size of the plate, if it wasn't much bigger than the magnet, would improve our model. But because we try to show the best possible version of such parachute to test if it is even possible or even practical, we decided to only focus on a plate that's much bigger than the magnet.
Right. Okay. No, I guess that could be another improvement which can be tested further with experiments. Okay, great. Okay, so while performing experiments, I guess the height, the difference between the plate and the magnet is very much less. But do you think any external environmental factors can affect that phenomena? I mean, is there a particular or if you think if it's being if the surface of the magnet is a higher surface area, to will how would you include the resistive forces or friction if you think it's important or not? I mean if for the first part of my point is, do you think it's important or not? And if it is, then how would you, include it in your particular model?
So we understood the problem statement to be asking if only a falling magnet without any additional improvements taking air resistance or other forces into effect. So we focused on only a falling magnet. We assumed that when we conducted our experiment, we assumed that the air resistance was negligibly low compared to the
Right. Okay, fine. Okay, just
dear reporter, could you say, could you show a slide with the height of the falling magnet as a function of a time?
Okay, just a second. So,
yeah, this no, the experimental one.
Experimental one. Okay.
Yeah.
So
the 10th slide, of course. Yeah. Okay. Thank you very much. Could you say what is the acceleration of magnet on this plot?
I sadly cannot answer that off the top of my head. But
so, as I calculated, it's somehow really near 9.8.
Oh, you mean the actual acceleration? Yes, the acceleration is the gravitational acceleration, of course. But
okay, so and when the magnet comes into effect, because I can't figure out anything about the effect from the problem from this plot, from the experiment.
Now we only saw an effect. We also could hear it, so that first tipped us off to it. But when dropping a single magnet from 5.4 centimeters, the top A plot, you can see a slight in the blue dots. They get slightly less steep towards the end of the fall. So that's it's questionable. It's there. If I could. Sorry, if I could show the video, maybe you could, maybe you would be able to see it.
Okay, no, it's enough. And the other small question is like, does the thickness of a plate affect the falling acceleration of a magnet or not? Or what the optimal thickness will be?
Now, in our model, we assumed a plate that has a very high conductivity. So the model doesn't take the thickness of the plate in the effect, but during our experiment, we only noticed it qualitatively that thicker plates.
Okay, Pierre-Louis, please, you can ask a question.
Yes, I want to continue on the same slide 10. So first, on figure A, when is the magnetic interaction kicking in? At which time would you say it's kicking in?
So after 0.10 seconds from the start of the fall, we believe that the slope changes, it tails off.
Okay. Do you have error bars in your figure?
The experiment was we had an issue. We could only record it 240 frames per second, which gave us for 5.4 centimeter drop height only above 30 points, and we decided not to plot the error bars, as it would make the graph very unclear. Because when you analyze the footage, the blur of the magnet was so large that we could only approximate its center of mass to track its movement.
Okay, and could you explain to me the difference between your prediction and the measurement in figure B? Because you say there is no effect in figure B. I mean.
Now, figure B. In figure B, our prediction predicts the magnet to be falling at 9.8 with a 9.8 meters per second squared acceleration. So, my best guess why the measured magnet falls faster is because we were unable to keep the magnets completely still while falling. They were rotating a bit a bit to the side and impacting the plate earlier than if they were falling flat, falling just flatly. So that's, I believe that's why there's a slight change. Also, it's very hard to hit the middle of the magnet when tracking its movement. That's why I believe the
All right.
difference is there.
Okay, thanks.
Okay, thank you. Can Van Louis please ask a question then?
Okay, hello.
You also
So
sent
I
on the
have
chat.
two questions that for the reporter. So do you have the movie the video for this for your experiment?
I do. Just give me a second. I need to.
Okay, does the magnet move along the horizontal direction? Yeah.
So do you want the wish? So this is the falling from around 5 centimeters, and the effect is noticeable slightly because we can compare it to. So I can show you a comparison to dropping it from a higher oh, I see that it is very it's very laggy. I apologize for that. My internet is
okay.
is not great. I'm very sorry for that.
Okay. But why did you do the experiment in the middle of the plate? Why did you do not do experiment where drop the magnet in the middle of plate?
I believe we did. The perception on the video is not, on the images are not great because they were filmed from head on. It's hard to see, but I am quite sure that in the experiment we dropped it. We tried to drop it in the middle of the plate to ensure that the plate was indeed the edge of the plate were far away from the magnet.
But in your theoretical model, you take into account the plate infinity. I think you should, yeah.
Yes, and that I believe is the main drawback of our model, that it overestimates the breaking potential of the parachute because the infinite or very high conductivity is assumed. Now, in reality, with finite conductivity, the effects will be even lower.
Okay, thank you very much for the questions.